Hello, 5th grade. Today we're going to be continuing our study of chemistry, and we're going to talk about acids and bases. Now, when you think of acids, which is a term you've probably heard before, you probably think of a bubbling solution that's maybe glowing green, and then you might think of some of these caution signs like I have in the bottom right of the screen where they show an acid dripping on somebody's hand and it's eating away his thumb. And sure, there are some acids that can be like that. But not all of the acids that we're going to talk about are going to be quite that extreme, but it can still get you excited for this lesson. And bases is a word you've probably not heard before, and we'll go ahead and define that in a couple slides here. So let's get into it. So my first question is, what is an acid? We tend to think of it's some horribly dangerous, bubbly chemical that if you drip it on the floor, it's just going to eat its way down into the earth and just keep going down forever. And there's going to be a big hole left where it ate away through the floor. Or if you fall into a pit of acid while you're escaping some dungeon after stealing a sacred treasure or something, you'll fall into the bubbly acid pit and you'll be a skeleton in 10 seconds. And that's not exactly what an acid is. Those are kind of fantastical ways that we like to think about an acid. But scientifically, an acid is a solution, which is a chemical in water. So a solution is just when you have some chemical mixed up and it's dissolved in water. It's a solution that is ready to give up hydrogen ions for chemical reactions. So we've learned about our elements using our periodic table, so you should know what hydrogen is. It is symbolized with an H, and it is actually just about the simplest element that we have. It's just a single proton and a single electron. So when we talk about a hydrogen ion, we haven't talked in much detail about what an ion is yet. It's basically when an atom gets, or a molecule, gets extra electrons or it loses electrons, giving it a charge of some sort. So remember, electrons have a -1 charge, and protons have a +1 charge. So an ion is just where the protons and the electrons aren't quite lining up, so it's kind of imbalanced. Now, in a hydrogen ion, the hydrogen atom actually loses its electron, and because it's just a proton and an electron, it's just a proton. So a hydrogen ion is another way of saying a proton. And I have a little bit of a demonstration, or a picture that demonstrates this. So here we have our hydrogen atom. It is just a proton and electron, and if we strip away that electron, we are left with just a hydrogen ion, and that is often symbolized with an H+. So all an acid is, it's a solution that puts hydrogen ions into the water, and they're ready to react with things. So there's lots of different chemicals that could be called acids. It's just a general category of chemicals, of a solution. Now, there's also the question of what is a base, because this lesson is about acids and bases. And a base is sort of like the opposite of an acid, but also just as dangerous, potentially. So a base is also a solution, and it's ready to use hydroxide ions, which are OH minuses. So it's an oxygen and a hydrogen with an extra electron. It's ready to use these hydroxide ions for chemical reactions. So both acids and bases are kind of ready to react with things if they can. They have, in the case of acids, hydrogen ions, or in the case of bases, hydroxide ions. Is that OH minus is called hydroxide. You don't need to know that, but if you want to know it, go for it. So acids and bases will actually neutralize each other. So if you have some strength of an acid and then you add the opposite strength of a base, they'll actually neutralize each other, and it'll be a safe solution. You just stick your hand in it and you won't have your hand burned away, hopefully, if you did it right. Acids and bases actually kind of have the opposite effect on each other. So they'll neutralize each other and make each other kind of safer in a sense. Here's a fun little cartoon of an acid giving a proton or a hydrogen ion to a base, and the base is very thankful for that. So that's often the way this happens, is you're going to have these proton donors, which means they're giving away protons, and then the proton acceptor, so they're going to take that proton, and that's how the acids and bases will kind of react together. And just, I want to point out what we get when we put this proton ion, that H+, with this OH minus. So we have a hydrogen plus an oxygen in the hydrogen, and those of you who have been paying attention in chemistry know that there is a certain molecule that we find just about everywhere, and that is H2O. So when we mix an acid and a base, we actually combine the hydrogen and the hydroxide, that OH, and we get two H's and an O, which is H2O, which is water. Now, in order to understand acids and bases, you need to understand this pH scale. And we're only going to talk in shallow detail about this. There's lots of math that can go into this as well. It kind of follows a logarithmic scale, but we're not going to worry about that in too much detail right now. But what you need to know is that the pH scale is a series of numbers that usually go from 0 to 14, and they tell you how acidic or how basic a solution is. So being more acidic means it has more of those hydrogen ions, that H plus, ready to give away. And more basic, it means it's more of a base, so it has more of those hydroxide ions ready to give away. So it's a way of telling how acidic or basic something is, and it usually goes from 0 to 14. I think technically we can get outside of that range, but just about everything that you're ever going to see is going to be in this range of 0 to 14. Now, this is going to sound somewhat counterintuitive, but the lower numbers are actually more acidic. So at the very left-hand side of the scale, we have the very strong acids. So 0 is actually a very, very strong acid. Right in the middle of the scale, right at 7, so halfway between 0 and 14, 7 is going to be neutral. So it's not acidic or basic. So exactly at 7, it's going to be completely neutral. It's not acidic, it's not basic. Water would fit in this category. It's not acidic or basic when it's pure water. Finally, higher numbers are more basic. So if you're up at 14, that's a very, very strong base and very dangerous. So the more toward the middle of the scale you are, the kind of lower key the chemicals are. But when you get towards either end, either towards 0 or towards 14, it's going to be much more dangerous and much more reactive. So this is your pH scale, and right here it's nice rainbow colors to help you visualize it. Remember, very left is strong acids, 7 is neutral, no acid, no base, and 14 is very strongly basic. Now, sometimes basic is called alkaline, so you might see that word thrown around sometimes, such as in this picture. This is a picture that shows you where several different substances that we see in everyday life, where they fit onto the pH scale. So as expected, right at 7 we have water. So water is very neutral. Notice it's right above the word neutral. Let's go in the acidic direction first. So milk is actually slightly acidic. It's at 6, which is not very acidic. That's why it doesn't seem odd when we drink milk. Coffee is a little more acidic than milk, interestingly enough. And then, believe it or not, tomatoes are actually acidic. And for those of you who ever have problems when you eat too much acid or something, you might know tomatoes can do that to you. And as we keep going toward the left-hand side of the scale, toward 0, the acids are getting stronger. So once we start getting towards vinegar, it starts to get a little bit stronger. Now, vinegar, of course, isn't the kind of thing that's going to burn off your hand. That's the kind of thing that we use to dye Easter eggs. So even down at pH of 3, we're not at anything too dangerous yet. But once we start getting in the 0 and 1 range, it's very dangerous. Lemon is often a classic example of a low pH fruit. And for the record, things that are acidic tend to have that sour taste, kind of like a lemon does. It kind of makes you want to pinch your cheeks together because it's sour. Now, interestingly enough, the things on the very left here I want to just talk about a little bit briefly. Stomach acid has a pH of about 1. You have hydrochloric acid inside your stomach, and it's actually a very, very strong acid. And that's what enables you to break down food when you swallow it. So you take a nice big bite of a hamburger or something, and you swallow it down, and your stomach acid is actually going to start breaking apart that food to help you digest it. And that's why when you throw up, sometimes it has that awful, nasty taste. Among other chemicals in there, there's acid in there, and that's not pleasant. And then to get really, really acidic, we can look at battery acid. So the liquid inside some batteries. It's very acidic. That's down at a pH of 0. Likewise, we could go in the opposite direction and look at things that are basic. So go back up to 7, to water where we're neutral. We can start getting more and more basic. So right next to 7 is blood. It has a pH of 8, and that's not too crazy. And then we have baking soda after that at 9. That's interesting. I think it's kind of interesting to think about, mixing baking soda and vinegar. You're actually mixing an acid and a base together. So that's kind of fun. And then number 10, that's interesting, stomach tablets. It's funny, stomach stuff appears on here twice. And that's not a coincidence. The stomach tablets are actually somewhat basic tablets, and so they can help neutralize some of your stomach acid. If you have too much acid in your stomach and it's making things unpleasant for you, you can actually take one of these stomach tablets and it'll kind of counteract some of the acid there and make it so it's not as acidic anymore. So that's how acids and bases can counteract each other to neutralize somewhat each other. Soap is actually a very common example of a base. Basic things often kind of have that slippery feeling, and soap certainly fits that category. Bleach is also on here. And one comment I want to make about bleach. If you ever do household experiments, never mix bleach and vinegar together. It'll produce a poisonous gas, and you do not want that. So we might be doing some experiments here at home over the next few weeks. Never mix bleach and vinegar together. Just don't do it. Stay safe. And now, up at a very, very high pH, up at 14, the highest on this scale right here, is drain cleaner. So that's the stuff you like pour into your drain to clean it out. So that's pretty powerful stuff if it's cleaning out the clogs inside your drain. So like Drano would be a brand name of that. Yeah, so just so you know, basic things tend to have somewhat of a bitter flavor. So I don't know if you've ever eaten soap, maybe when you were younger. It has that nasty, bitter flavor as opposed to acidic stuff that has a sour flavor. And if you're not used to distinguishing between bitter and sour, that's okay. Not a whole lot of people are, but lemons are sour, soap is bitter. Okay, now, what I want to leave you with here, after just this brief introduction to the pH scale and acids and bases. And actually, before I do that, one comment I want to make is where the term pH actually comes from. I forgot to mention that earlier. And you're probably wondering that. Why do we call this pH? And the reason we call it pH is it's actually short, it's an abbreviation of the phrase power of hydrogen. So remember that acidic things have hydrogen ions floating around. So pH is kind of the power of hydrogen. It's like how powerful are those hydrogen ions floating around? How many of them are there? And like I said, it follows a logarithmic scale, which is math that you probably haven't learned yet, so I'm not going to get into that right now. But it's a way of counting how much hydrogen or hydroxide there is in there. But anyway, so the thing I want to leave you with is an experiment that you can try at home using pennies. So what you'll need for this experiment is to find some old pennies, some vinegar, and some salt, which are usually pretty common household materials that you can find around. So most of you probably have these things. If you don't have them, that's okay. Maybe you can even experiment to see if something else will work. And old pennies, I don't know if you ever found an old penny on the sidewalk. It has that kind of nasty dark color, sometimes like stuff growing on it, and it looks like a million people have touched it, and it's kind of nasty. And actually what happens over time is it gets this layer of what's called copper oxide on the outside of it. So the copper, which is the metal that's on the outside of the penny, actually reacts with the oxygen in the air and produces this kind of, it's almost like rust in a sense, oxidation, which is called copper oxide, and that's kind of that darker color we see on some pennies. So, in this experiment, we're actually going to be cleaning pennies off using an acid. If you remember from our pH scale, vinegar is actually an acid. And so what we're going to do is we're actually going to mix vinegar together with salt. And the exact amounts don't matter that much, but in general about a quarter cup of vinegar and a teaspoon of salt would be good. So you're going to mix those together, maybe in a little bowl or a saucer or something. And then what you're going to do is you're going to put your pennies into that solution. And they don't have to be in there very long, even just about 10 seconds or so. And then you can take them out and rinse them in water. And one thing I like to do as well is actually just like dip half the penny in, and then you get a picture like what I have here on the screen. You get a penny that's half clean and half dirty. It's kind of cool. Then you can go buy something with it and confuse the cashier. So yeah, if you dip them into that solution, that salt and vinegar solution, it'll actually clean off the copper oxide. The acid will clean that off, and then when you rinse it off in the water, it should be pretty shiny, and you can enjoy the shininess. And if you need to do it for longer amounts of time, you can do that as well. So that's just a fun little thing you can do at home, and I hope that you enjoy doing that. I will also say that There's other things you can do with this experiment other than just making shiny pennies, though. If you try dipping the pennies into the vinegar, but instead of rinsing them off, you don't rinse them off, and you just let them sit on a napkin or a paper towel or something, and let them sit there for maybe a few days, you'll notice something start to happen to them. And I'm going to just tell you what the word is. I'm not going to tell you what it looks like. You're going to see something called malachite start to form on there. Malachite is a chemical that will start to form on there because you left the acid on the penny, and it's sitting out in the air and reacting with the oxygen in the air then. So you can try that as well, just letting it sit out. It might take a couple days or even longer perhaps for you to start to notice something. But if you have that acid left on the penny, I'm guessing you'll be able to see something start to happen. So you can have fun with that as well. And if you want to turn this into a true experiment, you can do a couple other fun things with this. You could test around and see if there's other ways you can get this to work. So we used vinegar in this model of the experiment, but maybe you could try some other form of acid, like maybe refer back to the pH scale and look for something else on there that could work. Like, maybe a lemon juice would work because we know lemons are acidic, or maybe tomato juice would work. You can experiment with some of these different things and see what works and what doesn't, and that'd be a good way to use the scientific method. Additionally, you could try varying the amounts of salt to see if that makes a difference at all. Or you could even try doing it on different coins, like does it work on a nasty old quarter, or does it only work on pennies? So there's lots of fun things you can do in this experiment, and I'm sure you could occupy yourself for a long time with that. One final fun point I will tell you with this is after you have put the pennies in and you still have that solution left, if you have put enough pennies in, some of the copper of the pennies might actually have been pulled out into that acid solution, and it's just kind of floating around in there. It's called aqueous at that point. You don't need to know that. But what happens then is sometimes if you put certain things in, like if you put like some nuts or bolts in there, the right kind of metal, that copper will actually be attracted to that metal. And if you, like say, put a nut or bolt in there, you might actually notice that when you bring it back out, instead of being a silver nut or bolt, it actually looks like it's a copper color. And that's actually because the copper was attracted to that metal and kind of stuck itself on the outside. It kind of plated itself on. So you have a very, very microscopically thin layer of copper on the outside then. So you could experiment around with that too, see if you can get that to work. And it may or may not work, just depending on the circumstances and the individual ways that you set it up and such. One point as well, don't use a metal bowl for this because that metal could interfere with the experiment. Use like plastic or something or some sort of ceramic, but not metal, especially not copper. But anyways, I hope you have fun playing around with this experiment. If you don't have the materials to do it, don't worry, you do not have to do this experiment, but it is a fun one to do, and pretty easy to do as well if you have the right materials. Well, I hope you enjoyed learning about acids and bases, and maybe next time you eat a tomato or a lemon or use bleach, you can think about the pH scale and where it fits on there. Anyways, I hope that you have a good weekend. Take care, everyone.